Hello, I welcome you all to this another interesting screencast. We have two problems that are coming from the Engineering Mechanics and Dynamics 14th edition by RC Hibbeler. In the first case, we have been asked to determine the speed when it reaches point B, the speed of the box. Okay. In the second case, we have been asked to determine the constant force. All right. So we are going to be using the principle of work and energy. So we have the initial kinetic energy of the box at A, and then the work done, total work done from A to B of the box, then equal to the final kinetic energy of the box. So in case number one, of course, we know that this for both cases is going to be equal to 0. The box initially is here, right? So when it moves to B, okay, what happens to the rope this side or the cord? Right, it will have moved as distance s or displacement s, and this displacement is just equal to the length of AC minus the length of BC, right? Great. Therefore, the work done, and when you look at the force and the displacement, both are in the same direction. Therefore, we have positive work, positive work. Okay, this is the force, and we have the displacement. So we have a 0 plus Fs equal to half mvb squared. Of course, in this first case there, we do have F, we do have S, of course M is there, then we are going to find VB, right? This will be found. Then in case 2, okay, the same equation holds, Fs equal to half mvb squared, right? We are finding F. We do have this, we have this, we have this, then we are going to find this, making it subject to the formula. So basically this is what we are going to do, right? So let's start the process. Okay, so case 1, and this is a 14-39. Okay, right? So what do we have here? Like we said, we have AB and we also have BC. This is the next point the box will have moved. Okay, right, and once that happens, it means the rope, this rope here, will have moved a certain distance s, or a certain displacement. And we need to account for that, right? Okay, so let's call this as our s. This is s, and this one is just equal to AC, the length AC minus the length BC. Does it make sense? Of course it does. Alright, so let's find what AC is. AC is just equal to 8 squared, right? 6 plus 2, 8 squared, okay, plus 6 squared. Okay, so this is AC, and then we do have a BC. BC is equal to 2 squared plus 6 squared, right? Great, there we go. So we already have S. So like we said, we are using the principle of work and energy. So the initial kinetic energy for the box at A plus the total work done from point A to B is just equal to the total kinetic energy at B. And kinetic energy is always positive. But when we look at the work done by the force, we have the force like so, the displacement like so, and this of course will give us positive work, right? Of course. So since our box, okay, starts from rest, this is equal to 0. Okay, right. Therefore, we'll have a 0 plus the total work, which is just F times S, okay? Then this is equal to half M mass of the box times VB squared. The force is given there, we have a 300, we have S, which we can just plug in. So we say this is AC minus it's AC minus right, let me just delete that. Okay, so it is AC minus AC minus BC, okay, and then this is just equal to half M, and our M is 75, then times VB square, and making VB subject to the formula, which you can do. Where is my calculator that you can do? So just grab your calculator. So 8 square root of 8 squared plus 6 squared, like so, then minus square root of 2 squared plus 6 squared, okay, then this times 300 and divided by 0.5 by 75, then square root of that, we have VB equal to 5.42 42 meters per second. Okay, so 8 squared plus 6 squared, square root of that, minus square root of 2 squared plus 6 squared, okay, times 300 divided by 0.5 by 75 and square root of that. Okay, so that's the solution for the first case. Then let's go to case number 2. Let's just create a boundary there like this. Let's go to case 2. So we have case 2 there, which is a 14-40. Right. Of course, in the second case, we have been asked to determine, we are determining the constant force. So there we go. We are using the same equation, work and energy principle, initial kinetic energy at A plus the total work done from A to B, and this is equal to half mv squared, like so. Like we said, this is equal to 0. Okay, so we'll have a 0 plus fs, okay, equal to half mvb squared, like so. Okay, so here the question is to find the force. So we have F times the same stuff, this stuff here, just collect it and then we can place it. Let me just wrap that and then just move it just there like so. Okay, and then maybe I move it a little bit back like so. So there we go. Then this is just equal to half times 75. Then here we do have the velocity of 6. So we'll have 6 squared like so. And therefore making F subject to the formula. This just gives us this just gives us so we have 8 squared plus 6 squared square root minus 2 squared plus 6 squared. Okay, all right, and then later on we have all that stuff and we divide that by answer. Then we have a force of 367.30 newtons. All right, I guess we are done. Okay, I think we forgot to include the free body diagram there. Now we'll have the weight acting through the center of gravity, and then we'll have the normal force, I think maybe somewhere there, to counter this effect here. All right, we'll have this effect here. If we are to include this here, is this okay? You see this, if we are to cut there, then you expect, again I'm just showing this, we are not using it anywhere, we expect to have this lifting force at this point. Therefore the normal force, so we have such forces like so here, so expect the normal force here to be somewhere a little bit far away, just a little bit far away, to equilibrate those forces, right? Okay, something like so. You have that distance somewhere there, just including it for the sake of including it. Let's call it distance x. Okay, all right, I guess this is about it. We have found, we just outlined the final solution. We have calculated the velocity in case number 1. We have also calculated the force in case number 2. So I hope this particular video was helpful, and if it was, give me a thumbs up. Continue subscribing and sharing my channel. All right, okay, so this one here is component of t. Okay, this is a component of t. So given if this is our theta here, okay, if this is our theta, let me say if this was our theta here, then this one just becomes a t cos theta, then this one becomes a t sine theta. Right, again, that information I'm just including it for the sake of including it. Right.